días. Espero que hayan descansado después de nuestra cena de la conferencia de anoche. Hoy es nuestro último día de conferencia, donde vamos a tener todavía el workshop de Ingeniería de Software experimental y el final del workshop de Ingeniería de Requerimientos. Hoy vamos a comenzar la jornada con el keynote de la profesora Carolyn Seaman, que está aquí conmigo, de la Universidad de Maryland en Baltimore County. Carolyn nos va a hacer una keynote sobre el tema de deuda técnica, Technical Debt. El título de la conferencia será Technical Debt at Decades of Research in Experimental Software Engineering. La profesora Seaman es profesora asociada del Departamento de Sistemas de Información de la Universidad de Maryland en Baltimore County. Es también Research Fellow en el Fraunhofer Center for Experimental Software Engineering en Maryland. Bueno, y tiene una larga experiencia en investigación experimental en ingeniería de software, especialmente en métodos cualitativos. En este año lectivo está haciendo una estancia en Recife, en el estado de Pernambuco, en Brasil, o sea que la teníamos cerca como para traer aquí a nuestra conferencia. Y bueno, los dejo con ella para que puedan aprovechar. Gracias.
Gracias. Buenos días a todos. Muchas gracias, Martín, por la invitación para estar aquí con ustedes y hablar un poco de un asunto que es muy importante a mí. Y he preparado la presentación en inglés y voy a hablar inglés, pero después, si quieren, si ustedes tengan paciencia con mi español malo y lentísimo, podemos tener preguntas en español y contestas en español. O si hay más paciencia conmigo, en portugués. Es aún peor. Okay. Thank you. All right. I think we covered all this. Let's see. Okay, I'd like to start with a quote that I'll walk through. It says, "It's only a little hyperbolic to call this a watershed moment for empirical software engineering study, where many areas of progress are coming to a head at the same time." Now, I didn't write this. It was written by Forrest Schall, a good friend of mine. He and I and a number of our colleagues at the Fraunhofer Center are in the process of writing a book chapter for a book that is being published later this year in honor of the 60th birthday of Dieter Rambach. So Dieter Rambach is one of the pioneers in empirical software engineering. He's been around for a while, and he's reached the ripe age of 60, so we're having a big celebration, and all of his friends are writing chapters to put together a book. So Forrest and I and some other folks decided to write about technical debt and to take a sort of holistic view of the role of technical debt in the history of empirical software engineering. So as I'm spending some time working on this chapter, I thought, well, why not make it into a presentation and present it to you today so you can see what we're thinking about. But Forrest wrote this sentence as sort of a theme for the chapter. So let me break it down, because Forrest has a very unique way of writing. So first of all, hyperbolic. Hyperbolic, I don't know if you have a similar word in Spanish or Portuguese, but it means exaggerated. You know, if you're feeling a little bit chilly and you want to be hyperbolic, you say you're freezing. Okay, so it's exaggerated. So it's only a little bit of an exaggeration to call this a watershed moment. A watershed is a place at the top of a mountain where the rain that falls on one side goes to one ocean, and the rain that falls on the other side goes to another ocean. Okay, so it's a place where things on one side are different from things on the other side. So if this is a watershed moment, that means that from now on, things will be very different than they were before. Okay, so that's a watershed moment for empirical software engineering. Hopefully you all know what that is. Many areas of progress, many different streams of research in our field are coming to a head, are coming to a point of maturity. Where we're really getting good results and have good understanding. And that's happening at the same time, right at the same time as we have this new problem, technical debt. It's not a new problem, but a new way of talking about it that can make use of that new point of maturity of all these streams of research. So that's what I'm trying to say here, is that we're at this right moment in history in empirical software engineering research to study this very important problem of technical debt. All right, so I'm going to start out by explaining what I mean by technical debt. and what the metaphor means and how it's been used, and also talk a bit about the research that's been going on the last few years and that is currently in process. And I'll talk about these streams of research that are maturing and how they're at a current point that's very useful for technical debt research. So I'll go through several of those. And also, beyond that, I think that the technical debt problem or the technical debt area presents a solution to some of the systemic problems we've had in our field in empirical software engineering for quite some time. So I'll talk a bit about that. And at the end, I have a call to action. I have things I want you to do. And we'll come back to this idea of whether we're really at a watershed or not. Okay, so what's technical debt? Let's start there. Okay, the context we're talking about is software maintenance. Okay, so we're talking about an organization that has lots of big, old, useful systems that they're trying to maintain. They have to be fixed, they have to be enhanced, they have to be adapted, they have to be constantly changed in order to keep them useful. Okay? And in general, these are, or especially we're talking about situations where these systems are big and expensive, too expensive to replace. So a lot of resources are spent in keeping them useful, keeping them going. Okay? So a lot of money goes into maintenance, but in maintenance, even more than development, and in software development, we're always talking about tight budgets, tight schedules. We have to cut corners. We have to save money. We have to be more efficient, more productive. And all that is true in development. It's even more so in maintenance. Okay, so this is the context. An organization's trying to save as much money as possible. They've got these big old systems that they can't just replace, so they constantly have to modify them for different reasons. So in that context, technical debt can be seen as a gap between two things. On one side, we have making maintenance changes, modifications to the software, making them perfectly, meaning making them exactly the way your software engineering professor taught you to make them. You know, preserving the architectural design, good programming practices, following all the object orientation rules, updating the documentation, and of course, testing it all thoroughly. Okay. On the one side, you have maintenance done that way. On the other side, you have doing it as quickly as possible, as cheaply as possible, just so it works and nothing more. Okay. Do you have this in Uruguay? Do you know what this is? It's duct tape. Okay. According to my father, anything in the world can be fixed with duct tape. Okay. So there's a software type of duct tape. Okay. And that's what we're talking about with technical debt. So one way to view technical debt is the difference between the way it should be done and the way it really is done. Okay, so when I'm visiting my industrial partners, I hear things or I read things, and these are the kind of quotes I see and hear when I know that technical debt is around. And some of these may look familiar to you. Some of them are about putting things off. Let's finish testing in the next release. It talks about what we're going to do later. Some of it's about the fragility of the code, how easy it is to break, and you know, the only one who can change this code is Carl. Nobody else even think about it because it'll break. Some of it's about bad programming practices like hard coding the password. You know, does anybody know where we store the password? Because it's in the code somewhere. It's not where it should be, right? The to-do, fix me comments in the code. I know if I touch that code, everything else breaks. Okay, we've heard that before. Don't touch that part. Oh, and this is the ultimate. You know, the release is coming up. Just get it done. I don't want to hear how you got it done. Just get it done. Okay, so these are everyday indicators, and these are the kinds of things that make practitioners know exactly what I'm talking about when I talk about technical debt. So, technical debt is a metaphor. Okay, it's not a new scientific theory. It's not a new concept. It's a metaphor. It's a linguistic thing. It's a way to talk about something. And if you were in Alberto's talk the other day, he mentioned that he found 11 different definitions of technical debt in the literature, which I'm not surprised. But they're all fairly consistent. Some of them draw the boundary a little bigger than others, but they're more or less consistent. The original definition that Alberto showed us in Spanish, I'll show you in English, or part of it, from Ward Cunningham in 1992, described it as an incomplete, immature, or inadequate artifact in the software development lifecycle. So it's something that needs more work, and that's where the idea of debt comes from. The developer is borrowing time and effort and resources from the system, holding back those resources, knowing that eventually they're going to have to pay it back later. So that's the idea of debt. You know, you get something in the short term, but sometime later you're going to have to pay it back and probably pay more because of the interest. Okay, so that was the original definition. So some of these other definitions in the literature are about things. You know, things, aspects of the software we know are wrong, things that are not quite right. And other definitions are more task-oriented. So things that we need to do, but we don't have time to do now, tasks that were left undone. But those tasks, because the fact that they weren't done is a risk that something will go wrong later. Okay, so those are definitions. There are benefits to technical debt, just like there are benefits to financial debt. If you go to the bank and take out a loan, the immediate benefit is you get to buy the car or the house or the vacation today, not in a year when you've saved the money. So that's a benefit, short-term benefit. For technical debt, the benefits are higher productivity in the current release. You get the release out the door faster. That's mainly it. And sometimes it even lowers the cost of the current release. Okay, so there are short-term benefits, but there are costs. Like in financial debt, the cost is you have to pay interest later. You don't just have to pay back the loan, you have to pay interest, some extra for the benefit of having the money sooner. So technical debt also has interest that comes in different forms. And then there's the other cost of debt, like financial debt. I'm sure you have this phenomenon in Uruguay too, when people just keep getting into more and more debt, they put more stuff on their credit cards, they take out more loans, and it gets completely out of control, and they have no hope of ever paying back all the debt. And we call that bankruptcy. And so there's something similar that can happen to a software system. The debt just gets out of control and it can no longer be managed. So that's an additional risk beyond just the interest costs of the debt. Okay, so I'm going to just talk a little bit very briefly about some of the current research in this area. It falls kind of into two categories. One is in how to identify technical debt, how to find it in a system. And the other is how to manage it once you've found it. So I could say a lot more, but I'm just going to go over this rather quickly. So if you're going to try to identify debt, try to find and discover debt, you have to figure out what type of debt you want to look for. And in the literature, there are all these different categorizations of technical debt. So there's design debt, which is probably the biggest category, or at least the one that's gotten the most attention. Design debt is debt that's related to the source code. Okay, and it could be at the source code level, it could be at the design level, at the architecture level, but it's related to the source code itself. Testing debt has to do with inadequate testing, and there are different ways that can happen. Defect debt are defects that you know are in the system, but you don't have time to fix them. So they're latent defects, and there's a bunch of others that have been proposed, and they're all over the place. So there are lots of different kinds of technical debt. Some debt's easy to find, and some is not. Some's fairly obvious. Okay, the easy stuff, test cases that weren't run. Okay, you ran out of time, so you didn't do this part of your test plan. Okay, and that's pretty obvious. It's, you know, people don't skip test cases by accident usually. Okay, they know they've done it, so that's pretty easy. Defects that are found but not fixed. Okay, if you have any kind of bug tracking, Bugzilla or whatever. You know which defects that you've already found, and you know which ones haven't been fixed. And there are always, not always, often in a system there are some classes, some parts of the system that everybody on the team knows they're a mess. They know they need to take some time to fix them, to refactor them, to redocument them, because they're spaghetti, they're in bad shape. But nobody ever has time to do it. Okay, so there's always some parts of the system that everybody knows are debt-ridden. Okay. But then there's other types of debt that are harder to find. Sometimes you have code that just very gradually decays and gets more and more messy over time, but it happens so slowly people don't notice. Okay, so that's one kind. Design patterns. A lot of times people use design patterns in the original development of the system, but nobody thinks to go back and check to make sure the design patterns have remained intact. Okay, so that's one kind of debt that can go unnoticed. And then we had examples of this in those quotes that I had earlier. Code that is so complex that only one person ever works with it. So that's the only person that knows how bad it is. Okay, so in general it's not known. And sometimes that person doesn't want to tell anybody how bad it is because for their own personal reasons, right? Okay, so identifying technical debt, whether it's hard or easy, depends on what type of debt you want to find. So you have to be a bit focused. So let me talk a little bit about some research we and others have done, in particular on design debt. So design debt, remember, is debt that's related to the source code. So there are different levels, different types of strategies for identifying technical debt, design debt. So one is automated static analysis. So there are a whole bunch of different ASA tools out there. We use one called Find Bugs, but there are lots of them out there. And an ASA tool runs through the source code and gives you a whole list of issues or warnings. These are places, specific lines in the software that the tool thinks there's something wrong with. Okay, so it's very, very low level. So, of course, the problem with ASA tools is that they give you this huge long list of issues and warnings, and not all of them are important. So we've done a little bit of research on this and tried to figure out what types of warnings tend to be more closely related to technical debt than others. And we haven't done a lot, but one category that's in Find Bugs is called multi-threaded correctness. And that tends to be one that is related to parts of the code that do cause maintenance problems later. So they're more likely to be real technical debt. Sort of the next level up are code smells. So code smells are violations of good programming practice that you can detect automatically in the source code, but they're at the method and class level. So they're not individual lines. It looks at whole methods and classes together. So it's a little bit higher level. We've done some research on code smells, and there are a couple that we've found have been closely related to technical debt. One is God classes, another is called dispersed coupling. God classes are classes that just are too big and do too much, and they should be refactored to make more smaller ones. So that makes sense. God classes tend to be more defect prone and tend to need more changes over time. So, so that's an indicator that they do have debt, have design debt. The other is dispersed coupling, which is one type of complexity. There are numerous different code smells that deal with complexity, but dispersed coupling is the one that we've found related to technical debt. Grime. Okay, one really fun part of doing research in this area is there are all these interesting metaphors, you know, so we've got grime and we've got smells and we've got rot and we've got all these interesting things. So when you come up with a new idea, the trick is to come up with a really yucky name for it and everybody will notice. So anyway, we have grime. So grime is when a design pattern breaks down. Okay, so you start out with a nice clean design pattern and all the code is perfectly arranged just like it has in the textbook. And it's lovely. But over time, you know, other code gets added that breaks the integrity of the pattern. And then we have rot. Rot is where the design pattern is no longer recognizable at all. Okay? So there hasn't been a lot of research on grime, but what there is has shown that grime seems to be related to testing debt more than design debt. So code that has a lot of grime is harder to test, takes more effort to test. Okay, and then on the either higher level, at the architecture level, we have something called modularity violations. And there's been a lot of work actually at the architecture level that modularity violations is sort of the first one that's really been empirically investigated. But there are other sort of proposals out there for finding architectural problems. There's even starting to be a catalog of architectural smells that are like code smells, except they're at the architecture level. And people are starting to play with those and empirically test them to see if they're related to long-term maintenance problems. But modularity violations are where you look at the change history of the modules in a system and determine where two modules get changed together a lot of times. Okay, so two modules have a dependency if they're always changed together. Well, if those dependencies are different than the dependencies that are defined by the architecture, then that's a modularity violation. So if there are two modules that should not be related according to the architecture, but they change together all the time, that's a violation. And that's been shown, actually the empirical evidence is much stronger there than in other places, that modularity violations really are strongly related to higher effort and more defects later during maintenance. Okay. All right, so that's just a really quick snapshot of a lot of research that's been done, a lot of the empirical research that's been done in looking at technical debt at the source code level. Another area that we're starting to look at is on looking at tools versus humans in terms of identifying debt. Now, I should tell you the story of how I first was introduced to the concept of technical debt. I was visiting one of my industrial partners, and we were in a meeting, and we were talking about something else. But they kept using the term technical debt. And so finally I said, what's technical debt? I don't know what that is. And so they explained it to me. And you could tell as they talked about it that there were two things I noticed. One, it was emotional. Okay, there's an emotional, it's like a guilt about technical debt. You know, they knew it was important, but they felt bad about it, you know, that they had technical debt. The other is when they talked about managing it, they even put their hands here. This clearly was where they managed technical debt, not here, but here. So they just had a gut feeling about where the debt was, how important it was, and what they should focus on. The other thing was that they all had a TD list. It wasn't a technical debt list, it was a to-do list. And it was, you know, stuck under their keyboards or post-it noted on their screens. But it was a list of the things they knew and felt bad about that they didn't have time to do. So classes that needed to be refactored, more testing that needed to be done, documentation that needed to be updated. So they all had their little list, okay? And that was how they managed technical debt. So I thought, okay, well, we have all these tools that supposedly will help us manage technical debt or identify technical debt. But what about these TD lists? What about the developers? You would think that maybe they might be the best source of information for where the important technical debt is. So we ran a little study, and I'd love to run more studies like this. This was a very tiny study. We had a small development group in a company, and they were all working on the same system, the same application. So we asked them, we gave them a template, and we said, if you had a week where you were not allowed to write new code, no new functions, no new enhancements, you're not allowed to fix any bugs, okay? All you have to do that 1 week is to improve the maintainability of the software product. What would you do? And we asked them to name 5 specific tasks they would do, each of them. So we had and there were 5 developers. So we had a set of 25 technical debt items, okay? Then at the same time, we ran an automated static analysis tool, a code smell detection tool, and we also ran some basic software metrics. And the question, then we compared the two, and we wanted to know, are the developers, the kinds of items the developers talked about, the things they're concerned about, were they also found by the tools? Okay, so what's the overlap? So do they find the same sort of things? And of course the answer is never, you know, never. It's yes and no. So the details are, the analysis tools found most of the parts of the code where the developers had identified defect debt and design debt. They found most of the modules that had defect debt and about half the modules that had design debt that had been identified by the developers. Okay, but the tools also found lots and lots and lots of other things. So the tools give you this, and within there are the little things that the developers thought were important. But if we hadn't had the developers, we wouldn't have been able to figure out which of those things was important. Okay, and then not surprisingly, the developers had several testing debt items and documentation debt items that they thought were very important, and the tools couldn't find that because they're not designed to do that. They're source code analysis tools. So, and we don't really have tools to find that kind of debt, but it's not that hard to find that debt. So it was interesting, and I'd really love to do more studies like this and kind of figure out what the role of the developers are in managing technical debt as opposed to tools. All right, so the other area where there's been some research is in the management of technical debt. So you identify technical debt, you have some indication of what's most important, then what do you do? Okay, how do you decide what to devote resources to? Okay, so once you identify technical debt, you have to evaluate the principal and interest, meaning the principal is the amount of effort that it takes to pay off that debt. So if you have an instance of technical debt that is about refactoring, okay, you have a class, you know it needs to be refactored. The principal is the cost to refactor it, how much effort it'll take to refactor it. The interest is how much harder it is to work with that module if you don't refactor it. Okay, so the extra effort of working with the code if you decide not to refactor it, that's the interest. So when you identify the debt, you have to have, we usually use just a high, medium, and low for principal and interest. It's really hard to put numbers on this, and you don't really need to. And then over time, you monitor those technical debt items. You discover new ones. Some technical debt items go away by themselves because you change the code for other reasons. And you look at your overall portfolio of debt to see if it's rising or lowering. And then finally, managing technical debt is all about making decisions about debt. Usually, in my experience anyway, there's more debt than there is time to pay off in a single release. So when you're doing release planning, you need to decide, okay, which debt is most important? Which ones are we going to focus on in this release? And it's not straightforward to make those decisions, especially because developers and managers tend to have different ideas about which debt is most important. So we wanted to tackle this problem and come up with a way to help project teams make these decisions and think about this. And we had no idea how to do it, so we thought, okay, what's the simplest possible way that you could do this? What's the simplest possible mechanism we could give to developers to do this? And the simplest thing we could thought of was just a cost-benefit analysis, where the principal is the cost of paying off an instance of debt, and the interest is the benefit, because if you pay it off, you avoid the interest. Okay, so the interest is the benefit. So you compare cost and benefit, you compare principal to interest of all the technical debt items. And the ones where the ratio is the most beneficial, those are the ones you pay off. Okay, it could not be more simple, right? But it's really too simple. Okay, it has lots of simplifying assumptions. It assumes that all the technical debt items are independent, which they're not. Some of them are interrelated. But it's a good place to start. Okay, so what we've done is we're running several ongoing case studies of several different types. Actually, let me talk about these first. The live studies are where we have this simple approach and we give it to a project team and ask them to try it and just see what happens. There we collect data on how much effort it takes, how much extra time during release planning do they take to talk about technical debt and to compare costs and benefits on effort, and then what problems do they have, because we want to know where this doesn't work. So this is to determine the costs of explicitly managing technical debt, to move the management from here up to here. Okay, so how much does that cost? And to determine where this approach is too simple. How do we need to modify it to make it more realistic? Okay, so we have several studies going on here. We've also done we've done one and are working on another retrospective study where we use historical data. And this requires a lot of historical data. So we need defect data, change data, effort data, the source code to run various detection techniques. So we can find in the history of a project places where technical debt was incurred and where it was paid off. Okay? And then we simulate what would have happened if a different decision had been made. So for example, we find in the version history of a system that there was a code smell. It occurred here, and here it went away. So at this point, either somebody made a decision or it happened by accident that the code smell was fixed. So we simulate what would have happened if that code smell had stayed there and the effort had continued to increase for modifying that. And then we can simulate in a very rough way the benefits of managing according to technical debt in terms of maintenance cost. Okay? So we have a couple very small retrospective studies. And this is to help us get an idea of what the benefits are of making decisions based on technical debt. Okay, so we have the two types of studies, one to look at the benefits of moving the management from here to here, and the other to look at the costs of doing that. Okay, and those are still ongoing, and we're not quite sure where they're going yet. So I don't have any results to tell you, but that's where we're starting with this very simple approach. Now, there have been some other approaches to technical debt management that have been proposed in the literature. As far as I know, none of them have been actually tried, but some of them are inspired by ideas from finance because technical debt is a metaphor with the financial domain. So in finance, we have things like portfolio management. We have options, real options. And those are things I don't completely understand because I'm not an accountant, but they're things that we can try to adapt and see if they might work in the software realm. But nobody's done that yet. Okay, so there's lots more to do in this area. There's lots of open research questions, and the point here is not to read all these. The point is just there are lots and lots of open research questions about management of technical debt. Is the simple approach enough, or is there something more complex we need to do? Can we borrow ideas from finance? There are open questions about identification of technical debt. What are the limitations of the tools? Do we need better tools? Do we need better ways to get technical debt elicited from people? There are questions about the social aspects of technical debt. We did an interview study a while ago, and an interesting thing that came out, not very many people mentioned this, but a few of the interviewees talked about morale and the relationship between technical debt and morale and how developers felt about technical debt. And it wasn't that having technical debt lowered morale, it was that having technical debt and not being able to pay it off lowered morale. Okay, everybody's got debt, technical debt. It's unavoidable, so that's not the problem. The issue is not being allowed by management or by circumstance to address it. Okay, that's what depresses people, depresses developers. So there's lots to do here. Okay, lots to do, lots of studies to be done in industry and in the classroom. Okay. So that's sort of the current state of technical debt research. That's what we've been doing the last couple of years. What I'd like to do now is take a step up and look at the role of technical debt as a research area in empirical software engineering in general, and particularly look at these contributing streams of research. So these are areas that we've been looking at for a while in empirical software engineering. Software aging and decay is an old idea, and risk management, these two are foundational. So technical debt in some ways is just a restatement of these two problems. But there are other areas, qualitative research methods, software metrics, program analysis, software quality. These are all things that we've been working on for a while, and they've been maturing, they've been evolving, and now they're at a point where they provide some solutions that are very useful in attacking problems in technical debt. Okay, so first, software aging and decay. So this is foundational. Software aging and decay really is almost another name for technical debt. Okay, it's just a restatement of those ideas. And aging, software aging, is another metaphor. It's a metaphor to human aging and how we all get a little more brittle and a little bit harder to change as we get older. And there's also some decay happening as we get older. So it's another metaphor. The results of aging and decay, an inability to keep up. So an inability of the system to keep up with customer needs. Okay, it becomes harder to change, harder to adapt the system. Reduced performance and decreased quality tend to happen. Bellotti and Lehman and Parnas were the ones who first started talking about aging and decay in the 80s and 90s. And Lehman's laws, hopefully you're familiar with Lehman's laws. Is it 7, 8 laws? And one of them is the law of increasing complexity, which says that the complexity of any system that is in use and that is being worked on and being kept up to date over time, that its complexity is going to increase unless you specifically do something to lower that complexity. And that's really talking about one type of technical debt, right, especially in the code. Okay, it's just going to become more and more messy unless you do some work to refactor it. So this was really visionary. This was before agile methods, before anybody talked about refactoring or anything like that. Okay, so that's aging and decay. It's where it all started. Risk management is another area that's foundational because really technical debt is one type of software risk. Okay? And a lot of different people have written about risk management within software engineering and outside of software engineering. So Barry Boehm is probably one of the most well-known writers on risk management within the software engineering domain. All of these authors talk about some sort of risk management process or cycle, and they use different words, but they all kind of boil down to these 3 steps: identify, assess, and manage. And so we've borrowed that terminology in how we think about technical debt. So you identify technical debt, you assess it, meaning you figure out what the principal and interest are, And then you manage it. You make decisions based on that information. So we borrowed that idea from risk management. And there are several risk assessment approaches in the literature. That means approaches for assessing the value of a risk, like risk exposure analysis. And we're looking at some of those as a way to assess technical debt items, see if that works. And the other one, utility loss, is an idea from risk management that we've borrowed to help us think about the interest. Because interest on technical debt is different than interest on financial debt. When you go to a bank and you get a loan and you take on a financial debt, you know exactly what the interest is. You know what the rate is, you know when you have to pay it, how often, and how much it's going to be. Of course, that's not the same with technical debt. You might not even have interest, okay? So there's a kind of uncertainty in the interest on technical debt. So we use the concept of utility loss, which is just the magnitude times the probability, and we use that to characterize interest on technical debt. Okay, quick time check. Good. Good. Okay, so let me talk about a couple of areas that have evolved in significant ways over the last couple of decades. We'll talk first about qualitative research methods in software engineering. So in the old days, there was a time when nobody used qualitative methods. In fact, there was a time when nobody in software engineering could spell qualitative, okay, much less knew what it meant. Okay, so there was a time when we didn't do qualitative research at all in our field. In the late 90s, people started doing it a little bit, and there were the first few papers published in the late 90s. Then in the 2000s was what I call the era of political correctness. This is when everybody talked about how important it was to do qualitative methods, how important it was for other people to do qualitative methods. Okay, so people weren't doing it too much, but they were talking about how important it was. And one effect of that was there were some special issues of different journals that had special issues on qualitative research, which was great because it got some really good examples of qualitative studies in software engineering in the literature, and that helped a lot. So now we have qualitative methods. They're accepted. They're fairly widespread. Not everybody uses qualitative methods, and that's fine. Not everybody uses quantitative methods either. But we have a toolkit. We know how to do it. Okay? So there are qualitative studies out there at this point. So that's the evolution of this area. So currently, we have a host of qualitative methods that we have in our toolkit as empirical software engineering researchers. We have interviews, we have analysis techniques, we have surveys. We know how to do all these things, and we could use them when they're appropriate. So that's great. There are good examples of qualitative studies in the literature, especially in these special issues that have come out in the last 10 years. There are many people in our field who are really good at this and can help other people along. Okay, so we have the expertise. And we're starting to go to the next step where we're looking at qualitative synthesis. Okay, so qualitative synthesis is when you have a bunch of studies and you want to synthesize them so you come up with results that aggregate the results of the individual studies. And there are methods for doing that quantitatively, but now we're starting to look at methods to do that qualitatively. So the bottom line is at this point in time today, hoy en día, we have the tools and expertise available we have qualitative tools and expertise to investigate questions of human behavior, which is what qualitative methods were designed to do, because human behavior is the most complex phenomenon that we can study, and context. Okay, and I'll talk about that more in a minute, but by context I mean you can study a phenomenon quantitatively, but it's difficult to figure out the context of that phenomenon without using qualitative methods. And that's particularly important in technical debt research. So why is it important that we've reached this level of maturity in qualitative research in empirical software engineering? Why is that important for technical debt research? Because technical debt related concepts are context specific. Okay? Technical debt is experienced a little bit differently in different organizations and different projects. In particular, a particular organization, the way they approach technical debt should be based on their goals, okay, and also what I call their pain points. Their pain points are where they experience pain, okay, because oftentimes the interest in technical debt is a form of pain. So when you ask them where do they have pain, what you're really getting is where they're paying the interest, which shows you what types of technical debt are most important to them. And that's different in every situation. So we need to find out what the context factors are when we're studying technical debt in a particular setting. We need to understand that context really well. And we can find that out in a number of ways. But in order to really make sure we get that context and all the relevant factors, we need qualitative methods. Okay, quantitative methods are just really not sufficient to do that kind of study. So fortunately, we have this problem at the same time as we now have the ability to use qualitative methods well as a community. So those two have come together quite well. And I think a lot of the research, and not a lot, a good part of the research in technical debt so far has been qualitative, or at least has had a qualitative aspect to it. And that's what has made it more relevant to practice and been more accepted by practitioners. So the bottom line here is I think that we can't study technical debt properly without qualitative methods, because otherwise we can't get that context piece, which is so important in technical debt research. And until recently, we weren't able to do that. Okay, 20 years ago, we didn't have the expertise, we didn't have the tools, we didn't have the examples in software engineering of using qualitative research, but now we can. Okay, so that's one example of a stream of research in our field that is just at the right point of maturity that we can take advantage of it when we're looking at technical debt. Okay, another area, software metrics, which has also evolved a great deal in the last few decades. So in the 1970s, we started having the first metrics, which were complexity metrics. Halstead and McCabe are the most famous ones, where we started quantifying how complex, how interdependent a system is. So then in the 1990s, software organizations started instituting metrics programs. So they started collecting and analyzing metrics data in a systematic way. And a lot of this depended on the publication of the GQM strategy, the goal question metric approach, which happened in the early 90s or late 80s. And that helped a lot of organizations to come up with a good way to start a metrics program. So then in the 2000s, we started being a little more sophisticated with metrics. We experimented with different ways of visualizing metrics, so that made it easier for stakeholders to make decisions based on the data. And also dashboards. Dashboards are where you have different indicators, different charts and graphs that show you the current state of software metrics. And in some places, those are very highly developed and very tailored to a particular organization. And more recently, those kinds of visualizations and dashboards have been integrated into development environments. So they become even easier to use, even more part of the everyday work of a software development team. So currently, unfortunately, the adoption of software metrics in industry is still spotty. Especially in small and medium organizations, there are still lots of places who don't do software metrics at all, or do it poorly if they do it. But many, especially large development organizations, have become very data-rich environments. Okay, they collect a lot of metrics. They use fancy visualizations and dashboards. They do make decisions based on that data, and they do it well. They reason about it well. So a lot of places do it really, really well. And because some of these environments are data-rich, we as researchers, if we have access to it, we have a lot to work with in terms of empirical study. The other thing is that it used to be metrics were always an added thing. So it was a hard sell if I or another researcher or a consultant came into an organization and said, oh, there are so many advantages to collecting software metrics. You really should collect software metrics. Well, it was a hard sell because that meant it was an extra thing they had to do, extra effort, extra time, extra management. But now, because they're integrated into development tools, it's not really an add-on anymore. It's much easier to integrate that seamlessly into the development process. So the bottom line is that the tools are available to integrate data collection and managing that data into the software development process. It's possible to do it, and a lot of places are doing it, but not everybody. So why is this important for technical debt? Well, there seems to be a relationship between technical debt and software metrics, but it's complex. It's not straightforward. There have been things in the literature that have equated technical debt with high complexity. So they say, modules that have high complexity have technical debt. I don't think it's that simple. Okay, I think we need to investigate exactly what that relationship is. I don't think it's always true that modules with worse indicators, for example, higher complexity, will have real debt. And by real debt, I mean debt that will cause maintenance problems later, higher effort or lower quality later. Code smell definitions are one attempt to look at more complex relationships between metrics and debt. So code smell definitions generally are different combinations of metrics with different thresholds. So this metric is less than this threshold, and this metric is greater than this threshold, or this metric and this metric equals something greater than this. I mean, they tend to be these long Boolean expressions. But they combine different metrics and try to get at that complex relationship. So that's a step in the right direction. But in practice, often, and I've seen in a lot of organizations, the first step in managing TD is just look at the metrics, whether it be complexity, size, fan in, fan out, whatever it is, depth of inheritance sometimes, or even comment density. Some people swear by comment density. And they just look at those metrics, and that's how they identify their technical debt, which is a place to start. So the bottom line here is that the simplistic views of metrics are not enough. The relationship is more complex. We need to study it more. But as far as the maturity of the discipline in software metrics, we need these new tools, these modern tools that help us visualize and custom fit different ways of combining metrics in ways that are meaningful for a particular organization. Okay, another area that's really important that has also evolved is program analysis. So in the 70s, that was when people first started thinking about source code having properties in and of itself. It wasn't just something you wrote and ran and maybe tested, maybe not. But it had properties that you could look at and you could study. And they started with control flow and data flow. So somebody came up with the idea of control flow and data flow in the 70s, and they started analyzing that in larger pieces of software. In the 1980s, we had object orientation, and object orientation brought with it all these definitions of concepts that were supposed to characterize good design. Okay, things like inheritance, polymorphism, encapsulation, things like that, things that you could observe in the source code and use to judge the quality of the source code that you could analyze. And then in the 2000s, we automated some of that. Okay, so there became more and more static analysis and dynamic analysis tools. Things like code smells, things like ASA tools, a whole plethora of tools out there. So that was the tools era in the 2000s. And now some of those have been integrated into development environments. So that's sort of like in software metrics, that's sort of the current stage of maturity. So currently, there are tons of tools, tons of program analysis tools of all different types out there and available. Many of them, not all of them, but many of them are easy to use. Some of them are even free. And there are some cases, I'm not sure how many, but I've seen a number of cases where an organization has decided that the use of these tools is going to be an integrated part of their build process. And some of them even have thresholds. So they run something like find bugs, and they run it on the code just before the build. And if the number of issues is above a threshold, the build fails, even if it works. Okay, they say, no, it's an unacceptable level of quality because there are X number of ASA issues. So people are using them. Some people are using them. The problem is they generate mountains of information. And a typical ASA tool, you run it on any size software and you get thousands of these little line-by-line warnings. How do you know what to do with it? So that's the bottom line. That's the challenge. We've got the information. We've got all the information. How do you decide? How do you pick out the important things? And that's really the issue for technical debt. Okay? So you get a whole list of static analysis or program analysis issues. Somewhere in there probably are some really important instances of technical debt. How do you find where they are? And that's where, like software metrics, so the relationship between the kinds of anomalies that program analysis finds and technical debt is complex, and we need to figure out how to pick it out. So you can detect anomalies, things that are wrong, through program analysis, like code smells, like the warnings in ASA. It's not clear that which of those anomalies constitute real debt, and the tools are usually not very helpful in conveying the importance of different warnings. You just get a list of them, not ordered in any way, and it's hard to tell what's important and what's not. But program analysis, the tools and the techniques provide the building blocks for techniques that look at higher level concerns, especially at the architecture level. Okay, so they're very useful. So bottom line here is we have the tools that will facilitate identification of debt. We just need to figure out how to identify the gems, the needles in the haystack, okay, of all the information that we get out of program analysis. Okay, software quality. And this isn't so much about maturity of the research in software quality, but maturity in how we're thinking and talking about software quality. So in the bad old days, quality just meant no defects. So people counted number of defects. A low number is good, a high number is bad, and that was it. Okay. In the 70s, we started talking about the ilities. So the ilities are reliability, maintainability, usability, adaptability, portability. And all these ilities are different aspects of quality. Okay, so we started talking about that in the 70s and in the 80s. So a recognition that quality may be more than just number of defects. In the 2000s, a number of researchers started looking into something they called value-based software engineering. The idea that software provides not just function, but also value, and that you can put a value on different aspects of quality. Okay, so, and there's sort of this whole research stream that is developed out of that. And now that's led directly to the idea that I think is more prevalent now in our field, that quality is contextual. Okay, so that the different ilities that are important in different contexts are different. Some organizations are more concerned about some types of quality than others. And that the idea that different types of quality have different value in different settings is very important. That's key. So currently, still a lot of organizations struggle to define quality in a meaningful way. It was much easier back in the days when we could just say quality equals number of defects. That was easy. Okay, people could do that. Lots of organizations counted defects. It was easy to do. It's harder now because we as researchers can't tell an organization this is what quality means for you. They have to figure it out themselves because it is tailored. It is contextual. The maturity of understanding of quality varies. Okay, some organizations really spend time in figuring out what quality means for them, and they collect metrics based on that, and they make decisions based on that. In other organizations, it's not so good. But those who manage quality successfully, those places that really do it well, tie their quality indicators to business goals. Okay, so there is a conversation between the technical people and the business people to find out what really matters, what types of quality really mattered, and what they want the outcome to be. And it may be to make the most money possible. That's okay. That's a quality goal too. Okay? So the bottom line is that quality management, good quality management, is goal-driven. And this, of course, is important, again, for technical debt research, because technical debt is primarily concerned with maintainability, that ility. But the other ilities tend to be connected to maintainability as well. So it's a little more holistic, but the focus really is on maintainability, because real debt are things that will cause problems in maintenance later, that will make the system harder to maintain. The debt-related concepts of principal and interest are very much tied to the idea of value. Okay, so value-based software engineering and the ideas from there have a lot to contribute to how we figure out how to assess principal and interest for different types of technical debt. So the bottom line is we have a more mature understanding of quality in our discipline now than we did 20 or 30 years ago. And that's a good thing, because technical debt is a different type of quality. If you're really just concerned with number of defects, then you don't care about technical debt, right? So, so we need that sort of maturity of understanding of software quality before we can address the problem of technical debt. Okay. I'm going to take a commercial break here, just real quick. I'm going to switch gears in a minute. But now that you're all sold on what a great research area this is, and you're going to go out and do lots of research in technical debt, I want to tell you about an opportunity and invite you all to join us in Baltimore this fall in October. October 10th through 11th for the Empirical Software Engineering and Measurement Conference. A very important subset of the organizing committee is here in this room. So, there's a lot of relationship between this community and the eSIM community. Unfortunately, the deadline for full research papers is already passed, but mark June 11th on your calendar. That's the deadline for short papers and posters. And in addition, co-located this year with eSIM is a workshop on managing technical debt. So that we've had there's been a series so far of 3 workshops on managing technical debt, where one of the things we do is try and figure out a consensus definition, and as Alberto showed us the other day, we haven't succeeded in that, but we keep trying. The next technical debt workshop is next month at ICSE in San Francisco, and then there's going to be another one on October 9th in Baltimore, co-located with eSIM. So if you're interested in this, if you're interested in empirical software engineering in general, see if you can come to Baltimore, okay? And we would love to have you. All right, back to our regularly scheduled program. So to recap where I've come so far, I told you what technical debt is and sort of the current state of research. And then we looked at several historical evolutions of different research streams in empirical software engineering and how their current state of maturity contributes to research in technical debt. But there's more. But wait, there's more. I think that technical debt, or research in technical debt, offers an opportunity for us also to address a couple of problems that we've had as a community persistently in my career in the last 20 years or so. And there are 2 that I want to focus on. One is technology transfer, the idea of getting ideas and solutions from academia, from researchers into practice. So this is a picture of my university, by the way. This is a beautiful, lovely building. It's brand new. It's gorgeous. And I wish I could tell you it was the IT or computer science building, but it's not. It's where we eat. Okay, but it's a gorgeous building. But anyway, from the university into the thousands of technology companies that are out there that could use what we do, that we could be of value to. And this is a tough problem that we've had for decades. The other problem that we had is the evolution of the discipline. So I've shown you sort of the evolution of different individual streams of research in empirical software engineering, but I think we've had problems evolving software engineering as a discipline across the board. So let me explain what I mean by that. First, about technology transfer. Too few of us, some of us have had the experience of seeing our work, our discoveries, our results being used in a very successful, practical way by practitioners, and that's a great feeling. But more of us need to have that experience. Too few of us has that happen. And there are several reasons for that. One is that sometimes we don't start from a real problem or a real context. So sometimes academic research starts from the idea of the researcher instead of grounded in a problem that they observe in practice. Okay? And that's sort of a recipe for it not making that technology transfer successful. Another problem is vocabulary. We're academics. Sometimes we talk like academics, and sometimes the words we use don't translate, and sometimes the words practitioners use don't make sense to us. Okay? So there's a vocabulary problem. The other is, as academics, we have a certain set of skills. We're very good at some things. We're smart people. We're good people. But we're not salespeople, always. That's often not one of the skills that we have. And sometimes you have to be a salesperson to sell your ideas to practitioners. The other is, as researchers, we want to publish. And sometimes the requirements of getting something published are not the same as the requirements for acceptance by practice. Okay, so sometimes those 2 are in conflict. So there's lots of reasons for this technology transfer problem. So why do I think that technical debt might be a solution or a partial solution? Well, first of all, it gives us a vocabulary. As soon as I start talking about technical debt, whether I'm talking to researchers from academia, whether I'm talking to practitioners from industry, they know exactly what I'm talking about. Everybody knows what debt is. They know what principal is. They know what interest is. It's a common vocabulary. As long as we don't make it too fancy, it's something that everybody understands. And it's also something that practitioners care about. Okay, remember the guilt that those practitioners felt when I first talked to them and how they went like this? Okay, they understand it. They know it's important. So if you come to them telling them you have a solution to at least part of the technical debt problem, they're interested immediately. And it forces us as researchers to view the problem from a practice point of view, because it really is a practical problem. It's not a theoretical thing. It's not a new high-level concept or a new theory. it's a practical problem. So to address it, you really have to look at it from the practice point of view. So that's good for us. When you're working with an industrial partner and you want to apply some proposed solution to some part of the technical debt problem, you really have to start with where their pain points are. So it's always the first question I ask is, where's the pain? Because pain translates to interest. Interest points to where the important technical debt is. So you have to start there. And that's good, again, for us. That's a good practice for us because we should always start where the problem appears in practice. So research in this area in technical debt is by necessity and by definition grounded in practice, which inevitably will help with the technology transfer problem. Okay, evolution. In my opinion, and my retrospective view in my career, software engineering in general, not just empirical software engineering and not individual substreams, but software engineering in general has suffered from an inability to build on previous results. Okay, people tend to do a little work here and a little work here and a little work here, but it doesn't build up from the bottom as much as it should. And oftentimes, it's because we suffer from a lack of grounding in the literature. So people don't do enough reading of the literature before they start their own research. Now, recently, I should temper that. Recently, we've been doing a lot more systematic literature reviews and mapping studies, and that helps a lot, okay? But we need to be better at then, once you have that literature review, to build on it, to really take your research problems from the literature review, not use the literature review to justify the research problem that you've already picked. Okay, there's a difference in how you use an SLR. So previously I've shown you all these evolution slides and shown the evolution in individual areas, and those are examples of areas that work has been built upon, and those are good examples. What we haven't done is to cut across those areas. We need to get better at finding solutions in one area that can be applied to a problem in another. Okay? Combining diverse solutions to address a multifaceted problem, because a lot of problems are complicated and they need solutions from different places. And we need to see the relationships between different areas. Okay? And that's what we're not doing so well. I think technical debt will help us do that. It is a multifaceted problem. I mean, I've shown you all these different areas, and addressing technical debt requires solutions from all these different areas. Okay? So here's our chance to appreciate, to use the fruits of our labor over the last 30, 40 years in all these different areas and put it together to address a very real problem. Okay. So in case you're just waking up, we've been talking about technical debt. Hopefully that's not a surprise to anybody. I've explained how it's a metaphor. It describes a real problem in software engineering. I've talked about different areas that contribute partial solutions to the technical debt problem and how they've evolved over the last few decades and how they've kind of come all matured at a good point right now to help us address technical debt because of this level of evolution, is what I just said. And even beyond that, I think also addressing technical debt as researchers will help us address some of the systemic problems we've had in our discipline for a while. So here's what I want you to do. I want you to do more research on technical debt and submit it to ESIM or wherever, but don't lose the industry focus. I don't think this problem can be addressed in the laboratory, or at least only very small parts of it. Keep talking to practitioners. Learn how they talk about technical debt. So it's not hard. It's a very common vocabulary that we can easily adapt. And listen to where the pain is. Okay? The pain points to where the debt is. And don't reinvent the wheel. Read the literature. Adapt solutions from other places. Be creative. And you don't have to be an expert in all these other areas. Collaborate with people who are. I mean, I think technical debt is an example of a naturally collaborative type of research area. Okay, so are we at a watershed? Okay, is this true? Is it, how hyperbolic, how exaggerated is it to say this is a watershed moment? Are we really at a historical moment in empirical software engineering research? Will everything be fundamentally different from now on? Are we going to be changed people from this point on? Okay, maybe a little too much, but we have the right problem. We have a history of research that provides at least the beginnings of the right solutions to a problem that means something, that's relevant and practical. So it could be, puede ser, Could be. Okay. Thank you very much.
Bueno, estoy seguro que va a haber preguntas. Les pido que usen el micrófono para poder estar transmitiendo la mesa. Si tienen las mismas ganas de hacer preguntas que yo, seguro habrá muchas.
Hello. Okay. Hello, I'm Giancarlo from Brazil. First of all, congratulations for your brilliant presentation. I really didn't know about this subject. I think you have conquered a new, I can say, researcher in this area from now.
Okay.
It's very interesting. Yeah. Thank you. But how practitioners are receiving this kind of new approach? You know, how are they using the results or something like that?
Well, so far, I think, especially because the research in management of technical debt is still very, very new. And that, when I talk to practitioners, that's what they really want. I mean, they think it's great if I can provide a new tool, you know, and say code smell detection detects this kind of debt. And if that's a part of debt that's important to them, they'll take it and they'll use it. And that's great, and they're very happy with that. But then they come back and say, okay, but then what? You know, what do I do with that information? And that's what we don't have yet. So we're starting with this very simplistic approach, and I know it's not going to be sufficient, but I've talked a couple places into trying it. And they're a little hesitant because it is a little bit of extra work. But when I explain to them, okay, I'm going to measure how much extra work it is because I want to know if it's too much. You know, maybe it's okay to manage it here. Maybe that's enough. It certainly is cheaper and faster to manage it here. I think it's better to manage it here. But yeah, so practitioners, it's that management side. They know that's a hard problem, and that's what they're looking for solutions for. And they do like the tools part, and you know, they are hungry for solutions in that area. But what they really want is what to do with the information.
Thanks, Caroline. It was very open, very wide set of things, very interesting talk.
Thank you.
So, of course, I mean, you are just talking about technical debt. You are dealing with the main problems of software engineering in some way. So I have just one question that is related to our mainly working context. That is, before we call it conceptual schema-centric development, but is now under the model-driven engineering umbrella. And when we face the problem of technical debt, we use an argument that I want to share with you to see if you think that you agree with it or not.
Okay.
This is some way telling that one of the problems of the technical debt is the low-level strategy that most of the software production methodologies historically follow. In the sense that if you focus on programming, when you have to compare the real world requirements and the lacking conceptual model and the code, if there are problems, you must have a lot of work to synchronize in some way the product with the world. If you use a kind of conceptual model-based strategy, you start with a requirements model, and from the requirements model you obtain with a methodological sound the transformation, a conceptual schema that is again converted with the maximum degree of automation in a software product. This technical debt in some way would cannot disappear, but would be minimized. So this is our point, to say, okay, one way of facing from the research perspective the technical debt problem is to provide as a solution conceptual modeling-based software tools. I mean, do you think that this is correct, or is too much to say that, okay, we have the solution. The solution is use models, not program. We call, even when people talk about stream programming, we use the term stream non-programming. That, okay, if you program, you will have always this technical debt problem. If you model, and the model is the code, you will minimize it. Is it true, or is it not just so simple?
And a couple of things come to mind. So one is that I think using a model-driven approach like you're talking about, if you do it well, will eliminate a lot of the technical debt problems. I think that's true. But I think it can also introduce another type of technical debt. That is, if you don't maintain the models can break down over time or decay over time or not be maintained over time. So if that happens, then they no longer support the development as well as they did, and you have the other types of technical debt. So it's an approach that if it's done well, like many approaches, if it's done well, it'll work. There was another point in there I was going to make, but now I can't remember. But so I think I guess the question would be, from a practitioner's point of view, I think a lot of practitioners accept technical debt because they truly believe it will take too much effort to not have technical debt. So if you offer them a solution like model-driven development, if they're not doing model-driven stuff already, that will look like a lot of overhead, and it'll look like more work than just putting up with the technical debt. One thing we found across the board is the practitioners accept technical debt as a reality. It cannot be avoided. They truly believe that. So the question is not how to eliminate it, it's cost-effective ways of dealing with it. And cost-effective is important. So if they view, okay, if you tell them, well, if you make these conceptual models and all these other types of models up front, then you won't have the technical debt problem. And if they view this upfront work as a lot of work, they'll say, well, technical debt's not so bad. Maybe that would be okay. So it's all about the costs, and yeah. Okay. Thanks. Okay. What else? Anything else?
You said that at architecture level, you can estimate the technical debt with modularity variations.
Mm-hmm. That's one approach, yeah.
Yeah, and that's my question. I wonder if there are more approaches.
There are, and it's not an area I've been working in, so I'm not sure I can say much about it. But so people like Yunfeng Kai at Drexel University in Philadelphia, she did the modularity violations. But there are people at the Software Engineering Institute, where Bill Nichols is from, who are working at the architectural level, along with Philippe Cruchten, who's at the University of British Columbia in Canada. They're all doing some good work at the architectural level. Also, Nino Medvedovic, I think is how you say his name. He's in California at University of Southern California. He's the one who came up with the catalog of architecture smells. So there are people who are really very active in that area and coming up with approaches for finding debt at the architecture level. And if you want to ask me later, and I can write down some of those. But I'm not as familiar with their work as I should be. Okay, but there is stuff out there.
And another question, and this is a curiosity. If we compare the technical debt concept with other engineering, I mean, we talk now about software engineering, if we project that into other engineering, do we share the same problem, or other engineering, civil engineering, the car lines production, architecture, I don't know, they have also such a, I was wondering now, if we are sharing the same problem, because sometimes this is related to this discussion about what we do is really engineering, or is just hand script, software, hand script or software engineering. So sometimes we use the example of houses architecture. I mean, you build a house, you need the plans, but you realize that in reality there are a lot of problems. When you buy your house and you have problems, you realize that maybe they are not in the same. I mean, this is the question. How do we compare with how the technical debt concept compares when we apply it, we project it to other engineering?
That's a really good question. It's not something I've thought about a lot, so I don't know. But it's interesting to think about. I mean, earlier I had a slide with duct tape. And as I said, my father fixes everything with duct tape. So the house I grew up in had a lot of duct tape. It had a lot of architectural debt. But it never fell down. So did my father or other people who were working on the house, did they have a sense of when they had to actually replace the pipe instead of putting more duct tape? And I don't know. I think that's very much a gut management. But with a bridge or a tall building, a skyscraper, you can only use so much duct tape, right? So there have to be, I suspect there are ways of managing that, but I don't know. The
source of my question is that for years we are teaching that we do things very bad in software engineering compared to other engineering as architecture. And when I did myself at home 4 years ago a restoration, it was such a mess. I mean, I was realizing that all the thing, it was my beliefs about the purity of architecture was completely down in the sense that everything was wrong. This was making me remembering continuously the problems of software engineering with painting, with the things that they told that they did. And so I start to believe, and we have discussed that in some panels, that sometimes it's not so, it's different because we have big problems. But there are some problems that are also shared by other engineers. In some way.
An interesting aspect of that would be good to think about and good to sit down with other types of engineers to talk about is, my guess is that technical debt in software is more hidden, it's more invisible because software is invisible. But I don't know, I mean, you know, pipes and wires are all hidden in the walls. Maybe there's a lot of debt in there that we don't see. I don't know. That's a good question. Okay. Yes? How are we doing?
Thank you for the presentation.
Sure.
You said we need to identify the source of pain in the industry. And I'd like to know your opinion. What would be the main source of pain in the industry regarding technical debt?
Well, I really think it is context specific. So the pain points are different in different organizations. So I've talked to some where the pain is they always have a big surprise right before release. You know, something that they didn't expect fails in testing or somewhere. So it's those surprises just before release. That's their pain. Others, it's, especially if you talk to developers, it's just code that is so difficult to work with. The programming is no longer fun because the code is in such bad shape. That's the pain. For others, it's one that surprised me that I worked with was the latent defects, that they had so many minor defects that they decided not to fix, that impacted testing efficiency because they kept finding the same defects. And they were losing productivity in testing. So it's different in different places. Those are some examples of places I've talked to. In general, in the industry, I don't know that that's an answerable question. I don't think there's a general answer to that. It's different in different places. Thank you very much. Y gracias por preguntar en inglés.